Good afternoon, everyone. My name is Rez Mani. I work for Allied Scientific Pro, and the title of today's webinar is Laser Cleaning Method and Case Studies. We have done this webinar so many times, and every time we add new features to the webinar, in case somebody is participating it for the second time, the contents would not be repetitive. The webinar is being recorded, and the recording will be sent to you within a few days. And my email address is also mentioned here. If you have any questions, you can send me an email. We will also have a Q&A session at the end of the webinar, so you can feel free to ask some questions. All right, so let's see what we are talking about today. Today, we will talk about laser ablations, the basic principles that are involved, and the types of lasers that are used in laser ablation. And then we would move on to the laser cleaning, which is a subset of laser ablation. So laser ablation could have drilling, cutting, many different applications. So laser cleaning is one subset. And then we would compare it with other competing surface cleaning techniques, such as sandblasting, water jetting, etc. And we would move on to the physics of laser ablation, which deals with material properties and laser parameters that are suitable for cleaning a particular surface. Then we would explore different regions of the pulse, femtosecond, picosecond, nanosecond pulse, and see what the differences are. We would compare galvo and polygon scanners, and then we would move on to certain applications, such as these are some case studies that we have done. Perma-fixed nuclear decontamination facility in Richland, Washington was one. Testing at Canada Aviation Museum in Ottawa, removal of lead paint, polygon scanners, paint removal, and we would move on to laser cleaning of bacteria and virus infected surfaces. So throughout the webinar, I'll show some videos which will familiarize yourself with our laser cleaning system and make things more clear. All right, so what is the principle of laser ablation? Let's talk about that. So this is a process in which a high power laser shines on a surface and basically ablates material from the surface. It could remove a coating or rust, or it could also do drilling or cutting or other operations. So once the high power laser is focused on the surface, there are so many physical processes that are taking place. So there will be high temperature gradients, there will be high mechanical stress. In some cases, there will be a formation of a plasma, a shock wave, and then there will be a mechanical breakdown of the surface. So all of these processes are at work and make it possible for the laser cleaner to clean the surface. Both CW and pulse lasers are used, can be used for laser cleaning, but the focus of this talk would be on pulse lasers, simply because pulse lasers have more parameters that can be controlled, such as pulse width, repetition rate, but CW lasers only have the choice of power and wavelength. So let's go more into details of laser ablation to see how it works. So a laser beam on the left side, you can see a laser beam is being focused on metal substrate that has some coated layers. This could be paint, for example. Coating usually made of resins, the combination of resins, pigments, solvents, and additives. And this is all from a paper by Malaysian authors that did some work on car removal of paint. So there is the metal substrate and several layers of coated paint. And once the laser beam shines on this, the coating actually absorbs the laser beam energy and gets very, very hot. So this would produce a plasma and a shock wave, and that makes some micro explosions that cracks the surface and throws out all the debris. And that would basically cleans the surface. So it removes all the coated material from the surface, as you can see here. Here is another depiction of generation of this plasma, which is basically due to absorption of the laser energy by the coated layer, and then the follow-up explosion that removes the coating. Now, this is only one mechanism. At lower powers, you can also get photothermal ablation, so just evaporation of the coating. And depending on the type of coating also, you could have the laser beam going through the coating and reaching the metal substrate, heating that, and then the plasma generated by the metal could ablate the coating. And that's called a spallation process, which I'll talk about later. In case of paint on a car, for example, the absorption is by the coated layer, not by the substrate. So as I mentioned, laser cleaning is a subset of laser ablation and can be used to remove rust, paint, oxides, thin films. But one has to consider the properties of each of these films. They behave differently. Some films absorb near IR, some such as paint, and some other films are transparent to near IR, such as oxides of transition metals that you can find in nuclear power plants. So the mechanism could be slightly different. So when we talk about this flux, the plasma that is generated due to high flux of the laser, we can always look at this emission or glow from the plasma and get an understanding of what are the material that exists there. And that is the principle of a technique called laser-induced breakdown spectroscopy, or LIBS. So if you're worried about damaging the substrate, you can look with a spectrometer at this plasma and look for the substrate material, the spectral line. Once that is observed, then you know that you have hit the substrate, and you can move your laser beam to another spot or reduce the intensity. We have actually tried this technique with our laser cleaners to look at the spectrum of the substrate and basically stop the laser or move the laser when it sees that spectral line. And it has been pretty successful, and we are trying to integrate that into our system. Now, once we talk about the depth of ablation, so how deep the laser beam could cut into the material, that depends on the material properties and also on the laser properties, such as wavelength, pulse width, pulse energy. And we will discuss the physics of that later. Also, there's one definition of ablation rate, which is the total amount of material that is removed from the surface per pulse. So this is an important definition that we are mentioning here. So let's look at the different types of lasers that are used for laser ablation. So from the left side, we have the UV laser, which is called the excimer laser. And by the way, all these lasers have a certain laser medium. So this could be either a gaseous medium, such as in case of excimer lasers and CO2 lasers, or it could be a crystal, which is in case of neodymium YAG laser and Pi sapphire laser. So the idea would be to pump this medium to create population inversion. And there are different pumping techniques, such as electrical or using flash lamp or high energy electrons or another laser, basically. And this way you can get the laser emission. So when we talk about the UV lasers, these excimer lasers are pretty slow rep rate, maybe about up to 20 hertz. and they're quite expensive. But the advantage of using a UV laser is that it's good for certain applications such as lithography or UV lithography, which is using microfabrication to pattern parts of a thin film. And also the UVC radiation, which is from 200 to 290 nanometer, is good for killing bacteria and viruses. So it would kill the DNA. It will destroy the DNA of bacteria and viruses. But as I said, these lasers are quite expensive, and they're also not very compatible with fiber optics. The transmission of fiber optics is low for UV range. So you can have from 126 to 351 nanometer range. There are different lasers that you can purchase in the excimer laser type. Next, we move on to the CO2 laser, which is in the mid-IR wavelength at 10 micron wavelength. It's a very popular laser used in industry for cutting purposes, especially for cleaning. Also, it's very, very useful. It's a gas discharge laser. It requires a lot of cooling. It's a pulse nanosecond laser is available. You can also get the continuous wave or CW laser. So that's one laser that is quite popular. Moving to the next one, in the near IR region, you have the neodymium YAG laser that uses the neodymium YAG crystal. It could be pumped by a diode laser. It's a nanosecond, probably about 10 nanosecond pulse width. And you can also get second harmonics and third harmonics, 532, fourth harmonics also, 266 nanometer by using a harmonic crystal. It's very useful, and it could be used for LiDAR applications, for cleaning, for many other applications. And then finally, we have the Thai sapphire laser, which is another near IR laser, and that is tunable in the range 650 to 1100 nanometer range. It's a solid state laser and very short pulses, femtosecond. It comes in CW and pulse mode. It's very expensive laser and lower power, but it could be used for discovering the band gaps of semiconductors and also for some applications of laser cleaning. Aside from these four typical lasers, we also have fiber lasers that have gained popularity recently in the industry. And the difference is between this laser and the other laser is that they don't have mirrors. So the medium, the gain medium is the fiber itself, is some kind of a doped fiber made of ytterbium, erbium, thulium, and basically there are some inscriptions inside the fiber that acts as a grating, and that would only reflect one particular wavelength. So instead of having a mirror, you have an inscription, you have a diffraction grating that is inscribed inside the core, and that acts as a mirror, reflects one particular wavelength. The medium could be pumped by a diode laser, and all the radiation is contained within the fiber. So basically that gives a great flexibility to the laser, because you can turn it, you could twist it, and you can get to hard to reach places. So this is a huge advantage of fiber lasers, and they're more economical than CO2 lasers. They have good power, and other advantages include higher pulse energy, good beam quality, and variable pulse length. So that's a very good type of laser for cleaning, and this is what our system is based on as well, which I will show you in a later video. Okay, so let's move on to the next and look at the laser cleaning. What is laser cleaning? So you could remove rust, paint, other contaminations from the surfaces using these laser cleaners. And here is actually our system, which is a 100-watt system, and you can see this box has the all the laser engine, the pumping mechanism, and then there's a fiber optic cable. This is an isolator, which would not allow the radiation to be reflected back into the medium. And there's a galvo and a lens, which has a particular focal length. So you have to focus that on the material that you want to clean. So basically, to get a better understanding of how this works, I want to show a video of how this laser cleaner works, and is cleaning basically a rusty pipe. So let me get this video started. Just give it a second.
So you can actually see the plasma because the wavelength is invisible, it's infrared, but the glow is due to the plasma. And you can also see the stuff. There's a pump there. It's a vacuum pump that removes all the debris.
All right, so that was the video there. So you get a better understanding of what it looks like. And let's move on with the important parameters of the laser cleaner. So some parameters are quite important for laser cleaning, and some of these are the wavelength, which is heavily absorbed. Some wavelengths are heavily absorbed by some materials, and some others basically are not. They're not absorbed. So depending on what material you're cleaning, for example, if you want to clean metals, they heavily absorb in near IR, but they reflect most of the mid IR. But polymers, for example, paints, they absorb mid IR better than near IR. So these are all the factors that one has to take into account. What material you want to clean, what kind of wavelength you have to use. A pulse width, in terms of the depth of the ablation, how deep you can go into the material, depends on the pulse width. If you use a larger pulse width, you go deeper. So we'll get into physics of that and the dependence on it too. So you need to have a higher energy per unit area to ablate the material if you're using a longer pulse width, because the depth of penetration is higher. Pulse energy, the rate of ablation obviously increases with increasing pulse energy, and so that's another factor, and one has to be careful not to damage the substrate. The beam shape, depending on what you're cleaning, sometimes you're cleaning some artifacts that or historical structures that have a lot of details, so you need to use a small beam to be able to get to all the nooks and crannies. If you are cleaning a wall, for example, with no features, it may be better to use a linear beam with larger larger lengths. If you're using concrete or cleaning concrete, then maybe in order to get into the pores, better to use a smaller linear beam. So it all depends on what you're cleaning. And then the repetition rate comes into picture because once you increase the repetition rate, you increase the depth of ablation, which could reduce the threshold fluence due to heat accumulation. So that also affects your cleaning. All right, so next, let's look at some other important parameters. Scan speed, for example, is another parameter that controls the depth of removal, because the depth of removal decreases with an increase in scan speed, and that's understandable. You can see from this paper, it shows this depth of crater versus the scan speed. So once the dwell time decreases due to increasing scan speed, the depth of ablation would decrease. Number of passes, increasing number of passes increases the ablation rate, and one has to monitor the substrate temperature and make sure it doesn't melt. Here's the paper that has surface temperature of a metal. It's an experiment from steel substrates versus the time. And you can see that when the fluence is around 2.2, 2.3, below that or around that, then the surface temperature is about 1700 Kelvin, which is below the melting point of steel. But once you increase that to 3.5, suddenly there's a big jump in temperature, there's some melting that happens, and the temperature increases up to 3200 Kelvin. So one has to be careful about the fluence, the energy density that you're shining on the substrate, so that it doesn't melt the substrate and damage it. All right, so next one, let's look at the other competing methods of cleaning surfaces. There is the mechanical abrasives here on the left side, where a rotating disc basically scratches the paint or the contamination from a surface. The chemical methods, where you apply a certain chemical and then scratch it off with a tool. And you have all these methods such as dry ice, sandblasting, and water blasting, where you shoot a particular material from a high pressure nozzle and the impact would remove the coating. So in case of dry ice, it's a CO2 pellets that evaporate, and sandblasting, quite popular. It shoots the grit and sand, and water blasting is a high pressure water. So what are the disadvantages of these? The main disadvantage is that you would contaminate the environment, because you have to deal with all the secondary waste that is generated by these methods and clean them off. And especially if you're in a radioactive environment, the secondary waste could be radioactive and definitely has to be cleaned. You have to avoid this secondary waste to get into your power, to your water supplies and environment. And that's a tough challenge. It creates a lot of pollution and debris, which could be dangerous for the personnel. They require personal protection equipment. As you can see in these pictures, it could damage the metal substrates. If you're cleaning a car, for example, with sandblasting, you could damage the metal surface underneath. It's hard to automate this surface, and it's quite noisy as compared to laser cleaning. It's a comparison between the loud siren and background noise in a restaurant, for example. So if sandblasting is a loud siren, laser cleaning would be a crowded restaurant. This is the difference between the two sound levels. So next one, let's look at more advantages of laser cleaning. It's a non-contact process, only light hits the surface. There's low environmental impact. Solid waste debris is collected by a vacuum pump, and it's very selective, because certain parameters such as pulse width, wavelength, and rep rate, they can be tuned to basically be suitable for some material better. And I will show you a video over here of this Coke Zero can that has certain colors, the black, red, and white. And the video will show that laser cleaning would only remove the black. Although it's shining on other colors, it also only remove the black. So that's a big advantage. Localized action in case of chemical cleaning, this could actually go and clean other parts, but in case of laser cleaning, it only cleans the area where the light is shining. Controlled removal, when you have proper parameters adjusted, you can just remove a certain thickness as you basically desire. So let's take a look at this Coke Zero. Let's take a look at this Coke Zero video. And that shows the selectivity of the laser cleaner. Just 1 second. This video does not have sound, so you will only watch it. So here you can see that the laser cleaner is shining on the Coke Zero, and it's only removing the black paint, not the red paint or the white paint. And that is simply because the black paint has a higher absorption coefficient. So it is easily absorbed it easily absorbs the laser radiation. Red paint does not have as much absorption. So one question that someone asks in a previous webinar, is it possible to remove the red paint and not the black paint? The answer to that question is no, because if you tune the laser to remove the red paint, its absorption will be more than the black paint as well, so it will remove the black paint. So in both cases, if you use the black paint, if you tune the laser to remove the black paint, it would not remove the red paint, but you could tune it. You cannot tune it so that it could remove the red paint and not the black paint. So that shows the selectivity of the laser cleaner. Next one, let's move on to disadvantages of laser cleaning. What are the disadvantages of laser cleaning? So we talked about the advantages. Now let's talk about the disadvantages. First of all, there's a need for focusing the laser cleaner. So it's not like sandblasting where you can keep the sandblaster at any distance and pour that sand or grit on the surface. The laser cleaner has to be kept at the focal distance from the surface, and only then it could effectively remove the paint or the contamination. Then the other one is a lower speed. For lower power systems, the speed of cleaning is lower as compared to other methods. So a sandblaster could probably remove the material faster, but the laser cleaner is not as fast. So in order to address these disadvantages, there are some accessories that have been designed. And one of them is the picture shown here is a fume extractor nozzle, where you can see that the lens of the laser cleaner, and let me show you actually the laser cleaner one more time. You can see it here. There's this lens and the galvo system, and that one is just placed inside of this fume extractor nozzle that has these rollers. So if you roll these wheels on the surface you want to clean, then the distance of the lens is fixed, and that's at the focal distance. So it will clean the surface for you. You don't have to hold it with your hand, and then this way you can just clean it. And there's this pump also that removes the debris. The other concern about the speed and accuracy is use of robotics. So robotics are very useful in the operation of a laser cleaner, and they could make it much faster and remove the effort by the operator. So let's take a look at one of the videos where robotics is being used to remove some paint from a pipe. So let's take a look at here. Let's give it a few seconds to load, please. Okay, so this was use of robotics for holding the laser and doing a more accurate job and a faster job. Now let's compare the other methods of surface cleaning. There are some videos that compares sandblasting with laser cleaning, and in this case, it's cleaning a ship. So we have a video of a sandblasting operation for cleaning a ship. I'll show you that video first, and then we'll compare it with the laser cleaner.
So here you see a operator is removing the paint using a sandblaster.
That's quite a difficult operation. It would contaminate the environment heavily. Next, we would look the same operation using a laser cleaner. How does it work when a laser cleaner does it?
So all the debris is being collected by the vacuum pump, which is a thicker pump, thicker pipe in here, and nothing goes into the environment.
All right, so that was a sandblaster. Sorry, that was a laser cleaner. Okay, so let's move on. Let's now talk about the physics of laser cleaning and understand what are the important parameters and how do we choose the right laser for the right material. So when we talk about dependence of laser ablation on material properties and laser parameters, the important material properties are optical attenuation coefficient, thermal diffusivity, density, and heat of vaporization. And for the laser parameters, the type of laser, which defines the wavelength, the pulse width, the fluence, the energy per unit area, and the beam size are important. So looking at the picture on the right side, see a laser beam shown in orange is shining on the material in the box, and it penetrates a certain depth shown by L alpha in the material. That's called the optical penetration depth, L alpha, which is the inverse of the absorption coefficient, which is alpha. Now, for short pulses less than 10 picosecond, basically this optical penetration depth is the same as the thermal penetration depth. So that the heat does not go any further than the light goes. But if your pulse width is larger, then the thermal penetration depth, LT, would be larger than the optical penetration depth. So LT would be greater than L alpha. Now, this is for greater than 10 picosecond pulses. So this LT, which is the thermal penetration depth, is a function of the thermal diffusivity and the pulse width. So there's a pulse width dependence. The larger the pulse width, the larger is the thermal penetration depth. So if we define the threshold fluence as enough energy to be deposited per unit area to evaporate the material or to remove the material, this FTH, threshold fluence, is a product of the density, the heat of vaporization, and either the optical penetration depth or the thermal penetration depth. So for short pulses, it's a function of optical penetration depth. So it doesn't matter what the pulse width is. But for longer pulses greater than 10 picosecond, this threshold would increase with increasing thermal penetration depth, which in turn depends on the pulse width. So larger pulse width, larger threshold fluence. Now, going back to laser ablation, let's compare different time regimes, femtosecond, picosecond, nanosecond. So in case of short pulses, everything is clean. There is no melt zone, no micro cracks, no heat transfer to surrounding material, no damage caused to adjacent structures, no surface debris, no recast layer. But when the longer pulses come into picture, you have all kind of liquid physics effects that are happening. There's damage caused by adjacent structures, surface ripples due to shock wave, ejected molten material, recast layer, surface debris. So all of these micro cracks, shock waves, and heat affected zones, everything will take place when you have longer pulses. And in order to compare the results, here's a picture of 3 different lasers that cut the same hole, and you can see the femtosecond hole is so much cleaner, and the 80 picosecond and nanosecond ones, there's all kinds of debris and crater that is formed there and melting that has happened. So one has to take this effect into account when you're doing a laser cleaning, and longer pulses would have bigger thermal effects. Here's a long and short wavelength behavior. So there are 2 graphs that I'm showing. On the right side, we have the behavior of metals at different wavelengths. So you can see that metals generally have a low absorption coefficient at higher wavelengths, say at CO2 laser 10 micron. Most of the metals have very small absorption coefficient. But when you come to the shorter near infrared wavelength, this absorption coefficient increases drastically. So one has to take this effect into account that metals absorb more in near infrared as compared to mid infrared. On the other hand, when you go to some glass material or polymers, the absorption coefficient is larger at mid infrared compared to the near infrared. So the near infrared basically decreases, the absorption coefficient decreases in near infrared. So that gives us the idea that if you use a 10 micron CO2 laser and you want to remove a paint from metal substrate, you don't want to damage the substrate. It's a good choice because the polymer absorbs that wavelength of 10 micron, but the metal underneath reflects it. So that's one advantage of the CO2 laser over near IR lasers. But if you use the near IR laser, you have certain other advantages because they are compatible with fiber optics, they're fast, and you can also, as I showed you in the Coke Zero video, you could selectively choose parameters so that it does not damage the substrate, but you have to be more careful. CO2 lasers, they do it inherently, but for near IR lasers, you have to carefully choose the parameters so that it doesn't damage the underneath substrate. Now let's compare galvos and polygon scanners. So let's see what the difference is between galvo and polygon scanners. So normally most of the lasers have galvo scanners, as you can see on the left side, but as laser power increases, these galvo scanners become heavier and they cannot handle higher power lasers. So polygon scanners are more suitable. You can see in this picture the polygon scanner that has multi-facets. So you can shine a high power CW laser on this polygon scanner and that could handle the power. So whatever the scanning mechanism may be, the laser power should be delivered in an intense short time period so that the delivered energy remains in the removed paint and not transmitted or conducted to the substrate. So this could either be achieved by a short intense pulse or with fast scanning speeds that is achievable with polygon scanners. So what are the other advantages? We talked about advantages of polygon scanners. They're faster, they're lighter, and they could handle high power CW lasers, and affluent removal is also easier. So this slide shows some more applications of laser cleaning, cleaning of rust and sandstone, decorative steel, decontamination of nuclear power plants, leaded paint, and we already talked about some of these. We'll show you some videos of some others. Here is cleaning historical places. This is the obelisk of Sfera in Egypt that has been contaminated with nitrate and sulfate layers and has been cleaned with laser cleaners. Some of the other historical artifacts that has a lot of features have been cleaned, and this statue, half the face was cleaned. This one I'm going to skip. Laser cleaning of aircraft parts. So one question is that why can't one just paint over the existing layer? Simply because it would add weight to the aircraft. So one has to remove the old paint and then repaint that layer. So basically, as I mentioned, CO2 lasers are very useful. They have no danger of damaging the background substrate, but they are not compatible with fiber optics, and that's a big disadvantage. In this case, you can see robotics is being used to carry the lasers and clean different parts. But with the near IR laser, fiber laser, the flexibility of action is much faster and better, and you can also control the parameters so that the substrate is not damaged. Now, next one is laser cleaning for nuclear decontamination. So in Ontario, Canada, for example, the electricity is being generated only by nuclear and wind and gas, and basically no coal is used. There's no coal is used in Ontario for generating electricity. So 60% of electricity is generated by nuclear power plants. So we heavily rely on these power plants for generation of electricity. However, after 30 to 40 years, these power plants needs to be decommissioned. So because they develop crack in the structures and the pipes, they get rusty, and you can't just throw them out. You have to use scabbing to clean the concrete or decontaminate the pipes before dismantling, because there is a layer of cobalt 60. It's a radioactive metal with a half-life of 7 years. So you need to do that to be able to recycle the metal that is in the reactor for future use. Methods such as mechanical scabbing and water jetting has been used, but they produce a lot of waste, and this radioactive waste is pretty dangerous for the environment. So what happens in a nuclear power plant is the corrosion of the metal pipes releases these products, the metal pieces, into the coolant, and this gets recirculated in the reactor and goes into the active area of the reactor. It gets radioactive and then comes back outside of the active area, gets deposited on the metal pipes in the form of oxides. So the oxide layers on the metal pipes after a few years of operation are all radioactive, and they need to be cleaned. So laser cleaning is a really effective way of cleaning these metal pipes. In fact, what happens is the transition metals, oxides, they are transparent to the near IR lasers. So if you use a fiber laser, the beam goes through the oxide layer with no absorption, and then it gets to the metal, heats the metal, and generates some kind of plasma that would explode and remove these metal oxides from the surface of the pipes. This process is called spallation. So this is different from the car coating where the absorption was done by the coating. This is the absorption is made by the substrate, and then the generation of the plasma from the substrate removes the coating, and that's just called spallation. So let's look at some of our you can say laser cleaning systems. We have a 100-watt system shown on the left side that I showed already in the operation of the robotics. It's been in use for several years. We also have designed and operated the 200-watt system on the right side. It has a smaller form factor, it's narrower, more compact, and has twice the energy. You can look at the brochures on our Allied Scientific website. Also, we have designed a 500-watt system. This is two views, the back side and the front side. And you can see that the fiber optics is all being coiled and is all covered. This laser will be very shortly released, the laser system. It's being tested right now, so within a month it will be available for purchase. So this has a very high power of 500 watts, which is used for faster cleaning. So let's go on to do some test case studies. I want to show you some case studies. So there was a case study with the 100-watt system in the Permafix Northwest, where there are some radioactive and mixed waste treatment facility are being handled. So we took our 100-watt laser blast 100-watt system there, and the operation was done in a negative pressure room. So many different objects such as concrete block, several metal tools were cleaned, and every time a radiation engineer would measure the contamination before, and then after several passes would measure again, and every time the contamination level in disintegration per minute fell below 1,000 dpm. So it was quite successful. So in order to get a better idea of how this was done, we would just show you a video that we recorded from there. And let's take a look at the video. Just give it a few seconds. So here is cleaning a carbon steel plate. The radiation engineer is making the measurement. The carbon steel plate, the beta and gamma radiations are being measured. After 3 passes with the laser, the radiation reduced to 4,000 ppm. So some tools are being cleaned here. After 2 passes, it became less than 1,000 ppm. Here's a seat clamp is being cleaned. And I should mention that our engineer was outside of this negative pressure room giving directions to the engineers at Permafix, how to control the parameters. Is a cutting torch. And finally, here's a concrete block. You can see the beam is quite narrow so that it could penetrate into the pores. And after 4 passes, the contamination was less than 1,000 ppm. Okay, so this was all the measurements at Permafix. Now we have another case study. This was done at Canadian Aviation Museum in Ottawa, where you can see this engine that has oil and soot on it is being cleaned. So let's take a look at the Canada Aviation video quickly. See how oil and soot is being cleaned from an engine part. Okay, so that was that. I'm gonna have to speed up the presentation. So not going to show these videos because we're running out of time. So this was a video of removing paint, leaded paint, which was done at our headquarters at Allied Scientific, and a special type of filters had to be used, the BOFA filter. I put a link in here. It has a certain slots to make sure that all the microparticles are removed, because lead is obviously quite dangerous for the health and could be toxic. So it removed the leaded paint. And here is another video where we used the 200-watt pulse laser at 50 kilohertz with the galvo, the polygon scanner, basically. The polygon scanner, which moves really fast, is rotating very fast and generates all these lines. And basically it could remove the spray paint from the metal surface. And one video of cleaning inside a pipe. As I said, you could adjust the size of the beam and the shape of the beam. So here we made a circular beam that could go inside the pipe and clean paint inside the pipe. Some customers were even interested in mounting the laser cleaner on a crawler, mechanical crawler, and go inside the pipe. So this very nicely could remove the paint from inside a pipe by making a circular beam. So other applications of laser cleaning of composite surfaces. We have tried that, but the carbon fiber reinforced polymer CFRP is very, very popular because of its lightweight and material strength. But unfortunately, the near IR laser burns the fiber optic. So it would damage that. We've tried that and it would damage that. So the way to clean the CFRP would be either to use a femtosecond near IR fiber laser, which has a short pulse width, very short pulse width, so thermal effects are less pronounced, or a UV excimer laser. So our laser would not work for this application. And then there are other applications such as cleaning greasy surfaces and bacteria-infected surfaces. Here's a study that compared several different types of lasers, the CO2 laser, neodymium YAG laser, and UV neodymium YAG. So it was a third harmonic UV neodymium YAG. And it found out that it could clean the sticky biofilms from the surfaces. So the best laser that worked in this case was a CO2 because it evaporates water and bacteria live in water. So, but the other lasers also function pretty well. You can also clean greasy surfaces by basically this process of espallation, because these oxides could be all ejected due to these plasma explosions that take place. So for the food industry, using a laser cleaner is very wise. Finally, there was the talk about the coronavirus, and coronavirus has this fatty center with the proteins sticking out. So it is sensitive to heat. So any heat above temperatures above 57 degrees have been shown to kill the virus. So there are some studies by these Chinese scientists that talk about that. So this could be used for cleaning surfaces. The laser generates a few hundred K degree or even 1,000. So for cleaning operations after all the pandemic is over, laser cleaning would be very useful. So finally, we reached the conclusions, the end of the talk. I'll just go through this and maybe I'll show one other video at the end of that circular beam, which we did not get a chance, and then we do some Q&A. So what are the conclusions? So laser cleaning to the process of laser ablation is definitely more efficient, cleaner for the environment, less noisy, more economical, and it's a good choice. Use of near IR lasers with fiber optics makes the paint stripping or contaminant removal very flexible to clean hard to reach places. So all the CO2 lasers are better for cleaning paint on metal. The choice of fiber optics and fastness of near IR lasers make them a better candidate. So one has to take the material properties and laser properties into account, such as listed here for each material. Polygon scanners are a good choice for high power CW lasers so that they can clean faster and have a higher power. So I mentioned about CO2 lasers. And finally, laser cleaning could disinfect the surface from bacteria and viruses. It should be able to kill off coronavirus due to its heat. And this could be used for cleanup operation after the pandemic is over. So let me just go back quickly to one of the videos here that I didn't get a chance to show. I wanted to show the video of this circular beam right here. Yes. So I wanted to show this. Let's see. And then this is the last video. This video doesn't have a sound, so you could see that the circular beam is cleaning. It's cleaning inside the pipe. And one other one also, I want to show how this rail, which is rusty from a rail track, is being cleaned by the robotics. So rail track and
robotic is handling the laser.
so I'll stop here. Sorry for going 3 minutes above the time, and thank you very much for listening to this presentation. If you have any questions, please feel free to ask now. You can unmute yourself and ask now. And we also have this feedback form. If you could fill it out and with any suggestions or any way you can think of improving this webinar, I'll be glad to hear from you. Thank you very much. Please, if you have any questions, feel free to ask now.
Rez Karim, just for attendant for name Ablation 01, please can you give me your name and email, please? I think you use a mobile phone, but I don't see her name and email.
Yeah, caller 01. If you could just type, if you could just give us your name and email.
I don't have.
So are there any questions? All right, so if there are no questions, I wish you a good afternoon, and hopefully We'll have another laser cleaning webinar in 2 months' time. We repeat these webinars with new contents every 2 months, and we can get together again. Stay safe and have a good afternoon. Thank you. Bye. Thank you.